So we want to look at a force table problem, and when we're talking about a force table, is we have a, you can imagine if we're looking down on top of a force table, the force table has a little dot in the middle with a ring around it, and the ring has multiple lines, string lines attached to it that run over pulleys. And the idea is that if we're looking at a side view of the table, so now if we look at the side view of the table, there's pulleys attached, and these springs run over the pulleys, and these springs then have mass attached to them, and the mass, which is pulled down by gravity then, has some weight, or weight equals mg, and that weight applies the tension up here on the pulley, over the pulley, so there's some tension this way, so this is attached to our little ring, and there's tension in the spring that's caused by mg of the weight. So what we want to do is we want to look at attaching 3 lines to our little ring here, and we assume that the goal is to get the ring centered and have the system in equilibrium. So the sum of all the forces, so we remember that equilibrium is having the sum of the forces equaling 0. Now when we sum our forces, because forces are vectors, what we really mean is the sum of the forces in the x has to be 0, and the sum of the forces in the y needs to be 0. Because this is telling us that when we sum up all the forces in both directions, we have 0. So the system isn't moving, it's in equilibrium. And in this case, this would be considered a static equilibrium. So let's assume that when we define our force table, what we'll do is we'll call the x this way and the y that way. When we're looking down on the table. So let's just attach. We'll attach our first force over this way, and we'll call this force 1. And force 1, we'll assume it's at some angle of 20 degrees, and we will make force 1, we'll attach a mass of 100 grams. Now let's put force 2 somewhere strange for us. We'll put force 2 over here. So force 1 is kind of 20, but this is 0 degrees. It's 20 degrees above there. And this is 180 degrees on the force table. So let's assume that we're going to attach a force 2 over here. And we'll say that this angle is 30 degrees. And we'll attach force 2, and force 2 will be 200 grams. So we've attached force 1 and force 2. So now what we need to figure out is, we need to figure out where we're going to put a force 3 and at what angle. So we need to know the amount and the angle that we have to attach force 3 to bring our little ring into equilibrium. So how are we going to do this? Well, we know that when we need to add up all our forces so that they're in equilibrium, so that they sum up to 0. So the first thing we need to do is we need to break F1 and F2 into its x and y components, because we can only add components. So F1x is F1 times the cosine. So this would be F1x here, and that's F1y. And this would be the cosine of the point. And F2x, let's do F1y first. F1 will be F1 times the sine of the point. Well, we said that F1 then should be the mass, which we have to convert to kilograms, so it would be 0.01 times gravity. And this turns out to be then 0.98 meters. So when we're looking at our force equation, we have 0.98 times the cosine of 20. And this would give us, we can pull out a calculator, this would give us cosine. This would be 0.92. So we can repeat this for the y, where we have our 0.98 times the cosine times the sine of 20, and 20 times sine. This is going to be 0.34 newtons. So we can repeat the same process where F2 now is 0.2 kilograms times 9.8. So this should be just 0.98 times 2, which would be 1.96 newtons. And so we can calculate an F2, we can calculate an F2x and an F2y. But when we're looking here at F2x and y, we see that both of them point, this one points negative and this one points negative as well. So when we're looking at this, we know it's going to be something in the negative x direction times our 1.96 times the cosine of 30. And this one's also pointing in the negative direction. So it's negative 1.96 times the sine of 30. So this is going to be 0.867 times 1.96. And this is going to be 1.7 and 1.96. This is 0.98. So these are both negative because they're pointing both down and away. They're in the negative directions respectively. So when we're thinking about summing the forces, if we wanted our system to be in equilibrium in the x and the y, when we sum our forces, then we have to add them all up to 0. So if we're looking at the total, force table, then we have these numbers up here. So F1 x is 0.92, F1 y is 0.34, and F2x is negative 1.7, and F2y is negative 0.98. But that will give me the space I need to continue the problem moving forward. So when we're looking at the ring, we have to attach mysterious for the force. But we know that when we sum the forces in the x, what we have is F1x plus F2x plus mysterious F3x. Those all have to be 0. So when we're looking at this problem, what we know is that F3x has to equal negative F1x minus F2x. And this, because we know this, because these three have to equal 0. So if we subtract these two over to the other side, that means F3x has to equal these other two equal and opposite. So when we plug in some value, this means that we plug in our F1x and we get negative 0.92 minus a negative, which makes it positive 1.7. So when we add these two values up, we have 0.92 negative plus the 1.7. It turns out that this has to be 0.7. Now we can repeat the same thing in the y, where we sum the forces in the y. And when we sum the forces in the y, we get the same idea. We have F1y plus F2y plus F3y, these all have to add up to be 0. So we do the same thing. We say that F3y then has to be negative F1y minus F2y. So we can now plug in our numbers for F1y and F2y. And we get negative 0.34 minus a negative is positive 0.98. So this tells us that F3y has to be 0.64. So F3, in order to balance F2 and F1, F3 has some x component that points in the positive direction, and it has some y component that's positive. So it looks like F3 is somewhere over here, because it has to be pointing up this way, adding with F1 to counterbalance F2. So when we want to look at the magnitude of F3, to get the magnitude of F3, so let's have F3 up here, F3x, we said was 0.78 meters, F3y is 0.64 meters. So we can erase this and fill. So when we're looking for the F3 using the diagonal here, so we know that F3x is here, F3y is there, so that means that here must be F3. So we can move this over here, and this is F3y, so F3x, F3y, F3. F3 using the Pythagorean theorem is F3x squared plus F3y squared. So we plug in these numbers, and this is 0.78 squared plus 0.64 squared. And using our trusty calculator, you get 0.78 squared plus 0.64 squared. So F3 is the square root of 1.018, which turns out to be about 1.01 newtons. So if we wanted to know the mass of F3, we would use the fact that this 1.01 newtons has to equal the mass of F3 times gravity, which is 9.8. So to get M3, we can just divide the 1.01 by 9.8. And this turns out to be 0.01 kilograms, which would be 103 grams. Now to get our angle, we remember that theta is the inverse tangent of Fy over Fx. So it would be F3y over F3x. And so when we have F3y over F3x, and we take the inverse tangent of it, this would be the 0.64 over the 0.78. And this is telling us that tangent of theta is about 39 degrees. So we were in the guess, it was a little bit right with the angle. So F3 sits somewhere up here. If we attached 102 grams, 103 grams at 39 degrees, that would be where F3 would have to be placed to balance F1 and F2 and bring our ring into equilibrium. So when we were looking at this, the key is to remember that equilibrium means that the sum of the forces is 0. So you break your components into x's and y's. You calculate your x and y components for F1 and F2. You remember that means the sum of those, the F1, F2, and F3 equals 0. You then come in and you make those components to get F3x and F3y. To get the magnitude of F3, you have to use the Pythagorean theorem. Once you know that, you can back calculate the mass, remembering that weight is mg. And we found that to be 103. We then used our components to get the angle, remembering that the inverse tangent of the y over the x component of the force can give us the angle, and we found that to be 39 degrees. So to balance F1 and F2 and bring the whole system in equilibrium, a force of F3, which was 103 grams on a pulley at 39 degrees would balance.